This topic comes at the end of 3 lectures on molecular orbital theory. So if you've never seen molecular orbital theory, you'll probably find this a little difficult to understand. Whereas if you're a professional chemist, you'll see that I've oversimplified some of the topics to make them more accessible to students at this level. Students here are too polite to say this, but at other schools, this is the place in general chemistry where some students say,
"Ugh. This is so boring and theoretical. I'm never going to use it. Why do I have to learn this stuff?"
So, the next 15 minutes is about why I think this stuff is cool and interesting and important. Here's a sample of the copper-ammonia complex that we studied in lab a few weeks ago. And here's the electromagnetic spectrum in the visible region, the part that our eyes are sensitive to. So at what wavelength do you think this sample is absorbing the most light? Well, most people would line it up with the spectrum, line up the colors, and guess around 450, because that's where the blues line up. And most people would be wrong. Because as you can see from the actual absorption spectrum, which shows how much light is being absorbed as a function of wavelength, there's almost no light being absorbed at 450 nanometers. That's near the minimum of absorbance. The maximum absorbance is out here around 615 nanometers. That's where it's absorbing the most light. 615 is orange light. So if it looks blue, why is it absorbing orange light? Well, as you can see from the color wheel, orange is the complementary color of blue. So as white light is being shined on this sample, it's absorbing the orange and scattering back to our eyes not orange. So when we see something as blue, what we're really seeing is not orange, because the orange is what's being absorbed. So this shirt, which is not, I repeat, not Raven's purple, is absorbing the complementary color of purple, or yellow. Whereas in this attractive tie, showing the colors of the University of Illinois, where I happen to go to grad school, the orange is absorbing blue, and the blue is absorbing orange. The way we explain the absorption spectrum is using molecular orbital diagrams. Let's take this spectrum. Remember, the x-axis is in wavelength units. I'm going to turn it sideways and convert those wavelength units into units that are proportional to energy, called wave numbers. And then we're going to look at a portion of the molecular orbital diagram for the copper-ammonia complex, because it's a really complicated diagram. There are a lot more atoms than in anything we've looked at so far. But there's a whole bunch of lower energy orbitals that are all filled. That's kind of boring. And a whole bunch of orbitals higher in energy than anything shown here that are all empty, and that's kind of boring. And this is the pattern of the orbitals in the part where filled meets empty. And we can see that the energy difference, the amount of energy absorbed by this complex, is equal to the energy necessary to promote an electron from one molecular orbital to another molecular orbital. That's what the molecule is doing when it absorbs that energy. When it absorbs that energy, the photon of light that's absorbed promotes an electron to a higher energy molecular orbital, forming an excited state. What happens to all these excited states? Do they just keep accumulating? Do we run out of blue dye molecules in their ground states? If we did, it wouldn't look blue anymore. Let's review all the orbital energy diagrams that we've looked at in the course so far. A few weeks ago we looked at atoms. We did atomic orbital configurations, 1s2, 2s2, 2p6, and so on. And we could draw that in the form of an orbital energy level diagram. The one for sodium would look like this. And then we did molecular orbitals of homonuclear diatomic molecules. And here's that orbital pattern. You can see the example I'm doing is oxygen. And just now we looked at the ground state of the copper ammonia complex, and it has yet a different pattern of orbitals. But what these diagrams all have in common, because they're ground states, they obey the Aufbau principle, where lower energy orbitals get filled before higher energy orbitals. And they obey Hund's rule, where if you have several electrons in degenerate orbitals, they fill them one at a time with parallel spins. So every molecule that has a different shape has a different pattern of orbitals in the molecular orbital diagram. And I don't want to talk about one molecule in particular. I want to talk about molecules in general. So I'm just going to put up this generalized diagram that shows some filled orbitals at lower energy, and will show just the highest two, and some empty orbitals at higher energy, and we'll just show the lowest two. If we irradiate our generalized molecule with light of just the right energy, just the right wavelength, it will absorb that light and promote an electron to a higher energy molecular orbital, making an excited state. And one thing that excited state can do to return to the ground state is to emit light. That's called luminescence. It can do that in two different ways. The first is called fluorescence, which was originally named after its observation in a fluorine-containing mineral, but it really has nothing specific to do with fluorine anymore. What it has to do with is prompt luminescence, luminescence that occurs immediately as far as we can tell. It's actually within microseconds, that's millionths of a second, or even nanoseconds, that's billionths of a second. Notice that we used a down arrow to represent the electron that was moving from one molecular orbital to another to go from the ground state to the excited state. That's because there's a spin selection rule. The transition is only allowed if the spin doesn't change. The down arrow represents an electron that has an m sub s quantum number of -0.5, and that can't change in the course of the absorption for the transition to be allowed, and the same is true in the emission. Fluorescence occurs when the spin state doesn't change, going from the excited state back to the ground state. The second kind of luminescence is called phosphorescence, which was originally named after phosphorus. What we now call phosphorescence doesn't actually occur in phosphorus. What occurs in white phosphorus is something called chemoluminescence. Our definition of phosphorescence now is slow luminescence. Why is it slow? Well, we can understand in terms of molecular orbital diagrams. We go from the ground state to the excited state by irradiating with electromagnetic radiation of just the right energy, just like before. But in compounds that phosphoresce, that excited state relaxes to a lower energy excited state. And we can see why it's lower energy. The spins are now parallel, so it obeys Hund's rule. And we know that gives a lower energy state. And now this lower energy state is stuck because it can't emit light and get back to the ground state without violating the spin selection rule. So we call this a forbidden transition, which, as it turns out, doesn't really mean forbidden. It just means we can't do it through the most likely mechanism, so we have to find a slower mechanism to do it. So phosphorescent compounds linger in the excited state before they re-emit that light for milliseconds or even seconds. Phosphorescent compounds are the ones that glow in the dark. With luminescence, there's none of that complication with complementary colors. If something glows blue, it's because it's emitting blue light, about 450 nanometers. But most colored things don't emit light. My shirt certainly doesn't glow in the dark. What happens with most colored substances when they make excited states? Well, what happens when you walk barefoot on blacktop on a sunny summer day? Hot. Why? Well, it's like when you take a dollar bill and break it down into 4 quarters and break that down into 10 dimes and break that down into 100 pennies. That dollar is like the big chunk of electronic energy that went into making the excited state. And without emitting any light, That gets broken down into several smaller chunks of vibrational energy, molecules vibrating faster. And that in turn gets broken down into lots and lots of little pieces of translational energy, kinetic energy. And we know from the gas laws that higher kinetic energy translates into higher temperature. So black top is black because it's absorbing a lot of visible light from the sun, and it converts that light energy into heat energy. That's what happens with most colored substances, with most excited states. What happens when you walk barefoot on grass on a sunny summer day? Not hot. Why? Grass is green. That means it's absorbing red light from the sun and making excited states. What's it doing with those excited states? It's not emitting light. It's not getting hot. What is it doing? It's doing photosynthesis, which is an example of photochemistry, when excited states do chemical reactions that ground states don't have enough energy to do. Can you think of other important examples of photochemistry? Film photography is an example. The compounds in the film do photochemistry, and that's what initiates the process of recording the photograph. Any other examples? How are you looking at me right now? Vision is an example of photochemistry. There's a compound called retinal in your retina, which does a photochemical reaction when light hits it, and that's what initiates the process of vision. Not all examples of photochemistry are useful to us. What can happen when clothes, curtains, flags get too much sunlight? The colors can fade. That's an example of the photodegradation of dyes. So there are really important and interesting things that excited states do that we explain using molecular orbital diagrams.
Light, light, it scares away the fright. Soothing incandescence in the middle of the night. No more bed at sunset, much to our delight. You know we all adore it, but what the heck is light? Look at the electrons all happy in their shells, zipping right along, their life is pretty swell. Each one has their own amount of certain energy, and they will stay forever if you let them be.
This is so boring and theoretical. I'm never going to use it. Why do I have to learn this stuff?